Yeah. So today we will learn the Gramschmidt process. The Gramschmidt process produces an orthogonal basis of a inner product space. Okay. I have a vector space, then it has many kinds of bases. Okay. We would like to have a basis of this inner product space, and suppose the dimension of V is equal to n. We fix a basis of this inner product space, and we want to apply this process called Gramschmidt process, and it will result in a new basis. Okay, it will result in a new basis, so that the elements in this basis, the vectors in this basis, they are mutually perpendicular. Okay, and if we desire them to be unit vectors, we can always divide by their length and get a new basis. So whenever this condition is satisfied, that is the vectors in this basis are mutually perpendicular, then this is called an orthogonal basis. Orthogonal basis, okay, of V. And if in addition the vectors have unit length for each I, then this vector is called, or this basis is called orthonormal basis. Okay, we are used to orthonormal basis. Yeah, in R3 we work with IJK. Okay, IJK, the standard basis, and they are mutually perpendicular. They have unit length. So when we have an inner product space, the best basis to work with is an orthonormal basis. But a vector space comes with some basis constructed by some process. We can apply this Gramschmidt process to convert a given basis into an orthogonal basis or orthonormal basis. Yeah. So let us look at the formal statement of this. Okay. So suppose I have a subspace. I have subspace of this vector space. Okay, and I have a basis. I have a basis of this vector space also. By some method, I have access to a basis of this subspace. Okay, and suppose this is an orthogonal basis. Okay, W is a subspace. Its dimension could be 1 or 2 or whatever, but we have constructed a orthonormal basis of this subspace. Yeah, then there exist additional elements Wm plus 1, Wn of the whole space, so that W1 up to Wn is a orthogonal basis of V. So in other words, if I am given mutually perpendicular vectors, a finite set of mutually perpendicular vectors, then we can enlarge this set to a larger set which consists of n mutually perpendicular vectors. Okay, n is the dimension. Yeah. So we proved earlier that mutually perpendicular vectors are linearly independent. So if the vector space has dimension n and I have n mutually perpendicular vectors, they are going to be linearly independent, and therefore they will form a basis. So Gramschmidt process starts with one set of mutually perpendicular vectors, and then it can enlarge it to a basis of the whole space, so that vectors in this basis are mutually perpendicular. Okay, the proof will be an algorithm. We will produce an algorithm to construct such a basis. Okay, and by taking, say, one single vector, take one single vector which is non-zero, then it is automatically orthogonal. Okay, there is no other vectors to compare with, and it says, the Gramschmidt process says that I can enlarge this singleton vector to a basis of the whole space, so that it is an orthogonal basis. So starting with any vector, we can construct other vectors which are mutually perpendicular and they are all perpendicular to this single vector. So I say in three-dimensional space, what does it say in three-dimensional space? Okay, in three-dimensional space, it says that I can start with any vector. Yeah, I can start with any vector. Okay, and then I can enlarge this vector to a set of three vectors so that they are mutually perpendicular. Geometrically, what are we going to do? Yeah, I will take a plane which is perpendicular to this vector. Yeah, a plane which is perpendicular to this vector. Inside this plane, I will need two vectors which are perpendicular. So I will have three vectors which are perpendicular to each other, and in our three vectors which are mutually perpendicular are going to give me a basis. Okay, so this is Gramschmidt process is a generalization of that I can start with any set of mutually perpendicular vectors, then it can be enlarged to a set of mutually perpendicular vectors which will constitute a basis of the ambient space V. So let us see what the algorithm is. So this algorithm is called Gramschmidt orthogonalization process. So the input is a basis, yeah. Output is a basis again of the same vector space, okay, and it will be a set of mutually perpendicular vectors which will form a basis. Okay, so let us begin. So I am given a set of mutually perpendicular vectors which are forming a basis of W, and if W is not equal to V, then I want to enlarge this mutually perpendicular vectors inside W to a basis of V. So suppose W is not equal to V. Yeah, then there is a vector in V which is outside W. And we have seen that if I take a vector which is outside the linear span of given set of vectors, then this new set of vectors is going to be linearly independent. Yeah, this set is a linearly independent set of vectors. So it will form a vector space of dimension m plus 1. Yeah, it will form a subspace of dimension m plus 1, but this may not be orthogonal. Right? Vm plus 1 may not be perpendicular to these Wi's. Wi's themselves are perpendicular to each other, but Vm plus 1 is may not be perpendicular to W1 up to Wm, and so we would like to modify Vm plus 1 to get a set of mutually perpendicular m plus 1 vectors. So here we use this idea of projection. Last time I explained the idea of projection. So idea of projection was that I have a direction W and I have a vector V. Okay, then I can decompose this vector V into two components. One will be in the direction of W, which is called the projection of V in the direction of W. And if I subtract from V this projection in the direction of W, then I get a vector which is V minus the projection of V in the direction of W, and we showed that this is perpendicular to the projection vector. Yeah, and the formula for the projection it is derived by using dot product. Okay, here we are working in inner product space, and this is equal to inner product of W with V over square of length of V times W. So it is a scalar multiple of W. Projection of V in the direction of W is a scalar multiple of W, but that scalar is the inner product of W with V divided by norm of W square. Yeah. So if norm of W is 1, if it's a unit vector, then this is equal to inner product of W with V, yeah, times W. So PW V equal to this. Okay. So PW, the projection map is taking vectors and producing vectors which are in the linear span of W. This is a one-dimensional subspace. It is consisting of all scalar multiples of W, and input is a vector, output is a projection of that same vector in the direction of W, and this formula says that PW is a linear transformation. Yeah, this map which is projecting vectors onto this line passing through W is a linear transformation. Yeah, PW, the projection map from V to this subspace which is spanned by single vector W. This is a linear transformation. Yeah. So from the properties of inner product is linear in the second coordinate. Yeah, it is a linear transformation, and of course, what happens to W? Where is W mapping to? W is equal to inner product of W with W times W, and that is equal to W. So all vectors in the direction of W, they are fixed by the projection. Okay, geometrically this is clear. When I take a vector in the direction of W and project it in the direction of W, I get the same vector. Yeah. So this PW is onto, yeah, W is mapped to W. So any scalar multiple of W under this projection map is also mapped to the same scalar multiple. So therefore the image of the projection operator is this one-dimensional space. Okay, image of the projection vector is this one-dimensional space, and we know how do we define rank of a linear transformation. Rank of a linear transformation is the dimension of the image, and in this case dimension of the image is 1, because the image is one-dimensional subspace which is a linear span of a single vector. So rank of projection operator is 1, and what is the null space? Null space of the projection operator, it is set of all V, so that the projection along the direction of W is 0. Okay, and this is the set of all vectors in the whole space which are perpendicular to W. Yeah, they are perpendicular to W. So if say, let us say V1 in three-dimensional space, and my W is in the direction of x-axis. Okay, take a vector in the direction of x-axis. Okay, if my W is equal to just the unit vector I, then the null space of the projection operator with respect to this unit vector I is all vectors which are perpendicular to the x-axis, and that is the YZ plane. Okay, yeah. So therefore the null space is all vectors which are perpendicular to W. Right, but we know the rank nullity theorem. What is the rank nullity theorem? The projection operator from V to W, it says that the rank of the linear transformation plus the nullity of the linear transformation is equal to dimension of V, and therefore the nullity of PW is simply dimension of V minus rank of PW. Rank of PW is 1. Okay, so the nullity of the projection operator is 1 less than the dimension of V. Okay, so if V was R3, then the nullity is 2, and so the null space is a two-dimensional subspace, and you know that two-dimensional subspace is a plane passing through origin, and that plane in this case is exactly the vectors which are perpendicular to the given vector W. Okay, that is how projection operator is working, and we want to now exploit this property of projection operator, that if I subtract from V the projection in the direction of W, I get a vector which is perpendicular to W. So V minus the projection of V in the direction of W, this is perpendicular to W, and therefore this is always in the null space. This is always in the null space of the projection operator. Okay, so we will exploit these things to construct a basis, orthogonal basis. So what do we do? This is the first step of Gramschmidt orthonormalization process. Yeah. So we were given a set of vectors, and I have a vector which is outside this. Okay, outside this Vm plus 1. Okay. Now our subspace W is already provided with the orthogonal basis W1 up to Wm, and Vm plus 1 may not be perpendicular to these Wi's. What I can do, I can project Vm plus 1 in the each of these directions, okay, and add them. So take the projection of Vm plus 1 in the direction of W1, projection of Vm plus 1 in the direction of W2, and projection of Vm plus 1 in the direction of Wm plus 1. Okay, yeah. So V is the big space and W is the smaller space. Okay, and I take a vector and look at its projection in the direction of W1, look at the projection in the direction of W2, etc. The projection of V in the direction of W1 is a scalar multiple of W1. Projection of V in the direction of W2 is a scalar multiple of W2, etc. So when I add these vectors, of course, it's a linear combination of W1, W2, Wm, and therefore this is a vector inside W. Okay. So given a big vector space, I have a vector in that big vector space. I have a smaller subspace. So I always think of plane passing through origin, and I have arbitrary vector in R3. I want to project that vector inside this subspace. So this is the natural way to do that. Take the projection of V in each of the direction of the orthogonal basis W1, W2, Wm. Okay, and then take their sum, and that's a vector inside W, and this is called the projection of V inside W. Yeah. So this is what we are doing, and we take the projection of Vm plus 1 in each of these directions of the orthogonal basis of W, and subtract this from Vm plus 1. Okay, subtract from Vm plus 1. Yeah. Now this vector, let us see. If suppose this Wm plus 1, after I subtract the projections in each of the directions, suppose this Wm plus 1 is 0. That means Vm plus 1 is a linear combination of W1, W2, Wm, but that will say that Vm plus 1 is in the subspace W, but this is not correct. Yeah. So when I subtract the projections in the directions of Wi's from Vm plus 1, and Vm plus 1 was outside the subspace, I get a non-zero vector. This vector Wm plus 1 is a non-zero vector. Okay. Yeah. So there is this projection inside W, and I have subtracted that vector, and this vector is what we want to prove, that it is perpendicular to each of the Wi's. Okay. We will check that this is an orthogonal set of vectors. We wanted to enlarge a given set of vectors into a orthogonal set of vectors, and this is what we did. We constructed this Wm plus 1 from Vm plus 1. Okay, so let's show that this is orthogonal. Now W1 up to Wm, they are mutually perpendicular, nothing to check. We have to only show that Wm plus 1 is perpendicular to every Wi. Okay. Wm plus 1 is perpendicular to Wi for every I. So you take the inner product of Wi with Wm plus 1. We want to show it is equal to 0. Yeah. The definition of Wm plus 1 is, it is Vm plus 1 minus the sum of the projections of Vm plus 1 in each of the directions W1, W2, Wm. So Wi inner product with this vector, but inner product is linear in the second coordinate. Yeah. So this is equal to, I can split this as Wi Vm plus 1 and Wi inner product with these vectors. Okay, but this is a sum, this is a linear combination of W1, W2, Wm. This vector is some alpha 1 W1 plus alpha m Wm. Okay, so therefore I can again apply multilinear property of the inner product and get that this is this is equal to Wi. This sum can be taken out, but I know that Wi with Wj inner product, that is 0 when I is not equal to j. So only one term will survive here, and that is the scalar multiple of Wi. Others are scalar multiple of Wj, they are perpendicular to Wi when I is not equal to j. So I am left with this, okay. But Wi inner product with Pwi Vm plus 1. Yeah, what is that? They write the projection formula. Projection of Vm plus 1 in the direction of Wi is this vector. Take the inner product of Wi with Vm plus 1, divide by the square of length of Wi times Wi. Okay, this is a this number comes out of the inner product because it is in the second coordinate. Inner product is it is linear in the second coordinate, so this number comes out, and I'm left with Wi inner product with Wi, and that is equal to that is equal to this is equal to square of the length of Wi, and I'm left with Wi time inner product with Vm plus 1, and therefore it is equal to 0. Yeah. Okay. So I just substituted the formula for projection of a vector in the direction of Wi, and that led to the proof that this new vector Wm plus 1, which I constructed, okay, by subtracting projection of Vm plus 1 in each of the previous orthogonal directions from Vm plus 1, then this says that this new vector is perpendicular to the old vectors. And so now I have a bigger set of vectors which are mutually perpendicular. Yeah. Now you can repeat this process. Suppose this m plus 1 vectors do not span the whole space. Then there is another vector which is outside this. Now repeat this process, and to enlarge this to a bigger orthogonal set of m plus 2 vectors. Now this process cannot continue forever, because V is n dimensional. As soon as you get n vectors which are perpendicular to each other, then I would have constructed n linearly independent vectors, and these n linearly independent vectors therefore will form a basis of W, and that is called the orthogonal basis. Yeah. Yeah. So this is the Gramschmidt process. Yeah. This is the Gramschmidt process. So